Our next speaker is George Kontoudis, a postdoc, a University of Maryland Robotics Center postdoc that will be talking about his research. Full disclosure, he works in my lab.
Yeah. Yep. Yeah, so hello everybody, I'm George. I'm a postdoc in the Aerospace Engineering Department working with Michael Lotti in the Motion and Teaming Lab. So today I'm going to be talking about decentralized Gaussian process learning for exploration with multi-robot systems. So we live in the new era of autonomous systems where they exist pretty much everywhere in our life. And this is attributed mainly to three factors. One is computation and software. We have significantly better computation capabilities. And we also developed a lot of software libraries to work with. Next, we have huge developments in hardware and sensors. We developed a bunch of very accurate sensors recently, which can be exploited from autonomous systems. And finally, we have a booming development in the machine learning theory. So if you combine all those together, you can find some examples of autonomous systems in our everyday life, which is from autonomous driving, delivering packages with drones, and amputees wearing smart devices. So there's still some core challenges, though, in autonomous systems and learning. And these challenges arise from massive scale of noisy data. So we have decision complexity because of this issue. We also have unknown complex dynamics, which arises problem in uncertainty quantification, either from computer vision problems to weather forecasting. Next, we have very expensive hardware. I said that we have a ton of developments in the hardware development, but hardware is still very expensive, and it's not so affordable to all people. And finally, we have privacy and security issues in networks. So there are a lot of challenges in distributed systems and networks. So my aim is to bridge this gap between autonomous systems and machine learning. So this is the outline of today's talk. First, I'm going to give you some fundamentals of Gaussian processes. Then I will continue with Gaussian process training for multi-agent systems. Next, I will go to the next step, which is Gaussian process prediction for multi-agent systems. Then I will discuss active learning with Gaussian process surrogate models. I will give an overview of that, and I will summarize my talk and give some future directions. Now, starting with fundamentals of Gaussian processes, Gaussian processes is a powerful tool for machine learning and uncertainty quantification, and essentially we try to incorporate prior knowledge and data. So in the graphic you see here, we have the prior represented by a mean value, which is this solid red line, and then the uncertainty is quantified with this shaded area. So as we incorporate data to our data set, we reduce the uncertainty, and then we adjust the mean value to the values of the true data, assuming that we have no noise. So eventually, if you add more data to your regression problem, you have something like that. And this, it looks like another famous name for Gaussian processes is that they look like sausages. So it's a sausage-shaped like regression problem. And some notable applications is regression. Then you can find problems in active learning for adaptive sampling, and finally Bayesian optimization for black box functions. Now, more formally, we have a data set which has some inputs and some outputs, and this is the model that represents the measurements. Y is the measurement, Fx is a Gaussian process, a zero mean Gaussian process, and epsilon is the noise. Now, the most important thing in Gaussian processes is the kernel function or covariance function. I'm using the separable square exponential covariance function, which has length scale hyperparameters for each dimension to characterize the how bumpy is the function, the latent function in that dimension, and signal variance or scale. Then to build a covariance matrix, we add some noise, sigma epsilon. And the first step is to learn the hyperparameter vector theta. And essentially, we solve this problem over here, which is nothing else than an optimization problem. So Gaussian process training is essentially a constraint optimization problem. Now, having this vector theta and the data set we had before, we're interested about making predictions in an unknown location, which is the X star. And our goal is to find the predictive distribution at that location. So these are the predictive equations that characterize the mean and the variance in Gaussian process regression. Now these equations have several names throughout the years. They have been rediscovered. So they're widely known as Kriging equation or as best linear unbiased predictor. So this is my 3-slide introduction to Gaussian processes. And now I'm going to be moving to Gaussian process training for multi-agent systems. Now, the major problem of Gaussian processes is the computational scalability and space complexity. Specifically, it requires a cubic number of computations for the inversion of the covariance matrix, and also a quadratic number of space for the storage of the covariance matrix. Now, in practice, this means that with computations that we have nowadays, we can limit our regression problems to up to 10,000 observations. If we have 5 agents, this means that we can have up to 2,000 observations per agent. But now we have another problem, which is we need to communicate all observations to every other agent. And this brings a major drawback of Gaussian processes in multi-agent systems, which is the communication. So we had, computational complexity, space complexity, and now we have the communication complexity. So our objective is to synthesize decentralized Gaussian process training methods for multi-agent systems that maintains the accuracy of centralized methods. They are computationally efficient, and they require as little communication as possible. Now, to do that, we base our work on centralized Gaussian process training, and there is this super important assumption, which is called the independence assumption. Essentially, our main problem is that we cannot invert a very large matrix, and the way we move for that is that instead of inverting this kernel matrix, we split our data set to chunks, and then each chunk has a block, and then we invert these block diagonal matrices, and we ignore the off-diagonal elements. So it's an approximation. But this yields some very nice structure for the log likelihood, where essentially the log likelihood can be approximated as the summation of the local log likelihoods. Now, this is a very nice structure, and we can build on that with distributed optimization techniques. And the way to do that is that we use consensus alternating direction method of multipliers, and essentially we convert the global problem to another constraint optimization problem. Now this is the centralized optimization problem, and this is there is a decentralized expression of this problem. Now, what I want you to keep from this slide is that those two problems are equivalent if the graph is connected. So essentially, we have a decentralized representation of the consensus ADMM problem. Now the first method we propose is uses the exact consensus ADMM. And one problem here is that, again, I'm not discussing the details here, but one major problem here is that for every iteration of this scheme, we need to solve a nested optimization problem. So for every iteration, we need to solve an optimization problem on the top of that. To address this problem, we make a first-order approximation, and this kind of removes the computational scalability problem, but we still don't have a closed-form solution, and for every iteration, we still need to solve this nested optimization problem, but we have some room for research there. So here is the theorem we came up under some mild assumption, the hyperparameter update that meets a closed-form solution, which is this guy. And what I want you to keep from that is that we no longer have, for the second step of the iteration, we no longer have a nested optimization problem. It's an analytical solution, so everything can be computed much faster. Now, we still have this annoying conservative approximation for large fleets. And this problem arises because we made this assumption, this independence assumption at the beginning. So essentially, if we have a lot of agents, these blocks are becoming smaller and smaller, and then we ignore more and more off-diagonal elements. Now, to address this problem, we came up with this artificial data set. So what we do is that, let's work on this example here. Every color corresponds to a different agent, the data set of a different agent. So the idea is that we randomly sample the local data sets, and we form a new data set, which is these black crosses. And now we augment the local data sets with, let's say, the yellow one. It will have the yellow data points, and also it will have all the black data points. And now in this way, we give some global variability to our data set. And the way it works, the workflow, it's very similar. So on the left figure, we have the original decentralized method, where we have our local data sets, and then we communicate, and then we come up with a global Gaussian process, whereas with using this idea, we communicate at the level of the local data set, we form a new data set, and then we run what we did previously. Now, some numerical examples here. We use generative 2D random Gaussian process functions, and this is an example with 8,000 observations. We get similar results with higher dimension of data sets. The fleet size is 40 agents, and we have a path graph topology, and then we split our data in slices. And these are some random function representations, and for every random function, we run 100 iterations. Now, these are some results, and they're a little bit chaotic, but let me guide you through that. The x-axis of the box plots are the methods that we're using, and then the y-axis are the corresponding hyperparameters. And here we're measuring the accuracy. So the dashed line is the true value of the hyperparameter, and the box plots are like deviating from that value. Here in this table, we have, again, all the methods, and then we have the time that it takes to implement each method and the communication it requires for centralized and decentralized methods. Now, starting with the centralized method, we proposed one method which improves the model estimation accuracy. And then in terms of time, they require reasonable computation and minimal information exchange. Now, for the proposed decentralized methods, one of our methods is very accurate, and in terms of computational complexity and communication complexity, all of our methods can be executed really fast when compared to the global method. It's almost 3 orders of magnitude faster. And that was the training. Now we move to the Gaussian process prediction for multi-agent systems. The motivation is similar, but now the objective is a little bit different because we want to synthesize decentralized Gaussian process prediction methods for multi-agent systems that can achieve high prediction accuracy, they're computationally efficient, and they require as little communication as possible. Now, the idea here is to use some aggregation methods. So essentially, each square is an agent, and it has a local data set. it makes some computations, it communicates that computations to a central entity that aggregates everything, and then the aggregations are broadcasted back to each agent. These are the local computations that we need to do to each agent. And now the objective is to make the aggregation methods compatible in decentralized networks. So in other words, moving from the top figure to the lower figure. And the main idea is to use consensus and iterative methods for distributed networks. So we managed to decentralize a lot of aggregation methods. I'm not going to discuss them, but I'm going to discuss one very nice idea we had here, where essentially we use something which is called covariance-based nearest neighbors. So what we do here is that we have an example of 10 agents, and then we say that the first agent and the last agents, they do not have much to contribute to the Gaussian process prediction. So what we do is that we compute this cross-covariance element at the level of each agent, and then we say if this cross-covariance is below a threshold, then it does not take part to the Gaussian process prediction, and then we implement the regular decentralized method that we discussed previously, and finally we communicate the predictive distribution to the excluded agent. So essentially, we use the covariance matrix as a structure to identify which agents are statistically relevant to the Gaussian process prediction problem. And here is another example. We use the NASA JPL surface temperature data set, and those coordinates have 122,500 values. These coordinates are from East Coast to Mid-Atlantic and from North Carolina to New Jersey. And here is how the sea surface temperature looks at this area. So from this data set, we take 20,000 observations, and we evaluate our methods with 100 test points. We use various fleet sizes, and for each experiment, we perform 100 replications. Now here's some results. So the important thing here is that, this is the accuracy plot, and this is the uncertainty quantification. NLPD stands from negative log predictive distribution, and these are like different number of observations. So this is for 4 agents, 10 agents, 20 agents, and 40 agents. Now, the important thing here is that we have 9 methods, but you can only discriminate 3 different graphs. This means that all decentralized methods converge exactly to the value of the centralized methods, which was our initial objective. Now, some more qualitative results from the methods we proposed. 2 of them are very good in terms of accuracy, scalability, and communications. And also the nearest neighbor method that we proposed achieves the exact same accuracy with the method that uses all the agents with 42.5 agent reduction. Now moving on to active learning with Gaussian process surrogates. So this has a little bit of different philosophy. The motivation is the same, but now instead of having a very, very large data set, we aim to formulate small but yet efficient data sets that can give us very high prediction accuracy and also good uncertainty quantification. Now, the way it works here in the block diagram, the first step is that we form an initial data set, a small data set. Then we fit a GP surrogate model, which is Gaussian process training. And then we solve the expected variance reduction. So this is kind of similar to what Yannis mentioned before. So this objective here, what it does is it tries to find what is the point that if I sample in the environment, it will reduce the overall uncertainty. And this is the variance using the current data set, and this is the hypothetical variance if we add one point in our data set. So after we find the next sampling location, we give this information to our robot. The robot goes and samples the environment, and then we repeat steps 2 to 4. Now, the proposed method, what we did here is that we proposed a closed-form solution to the active learning con problem. And you can find me my poster for more details about this work. But here are some results. So we have 3 box plots here: accuracy, iterations, and time. And then we have 3 methods. This is our method for the accuracy. So we can see that our method is the most accurate among the other 2 methods. And then in terms of iterations and computational complexity, in low input dimensions, our method is more demanding. But then if you move to a higher input space functions, then in terms of accuracy, we still maintain the best accuracy, but now iterations and time are becoming either similar or even better for iterations. So a summary and some future work, some takeaways from the first part is that distributed optimization can be efficiently used for decentralized Gaussian process training, and that closed-form solution improve the model estimation. Second, for the decentralized Gaussian process prediction is that we can use consensus method to decentralize aggregation methods, and also the nearest neighbors produce identical results with significantly reduced involvement of agents. And finally, with closed-form solution of gradient, we can improve the prediction accuracy and reduce the computation in high dimension spaces. Now, some future work is that we are changing the structure of the active learning problem, where we don't close the loop at every optimization problem. We balance exploration and exploitation, in other words. And I have a poster where I discuss more details about it. And finally, we plan to work on decentralizing Gaussian processes to fit global surrogate models and to formulate decentralized active learning techniques for multi-robot systems. And with that, I'd like to thank you and answer any questions you may have.
Okay, we have a bit of time for questions, and I will see you back there.
Thank you for a great talk. So 2 questions, actually. One is, do you think you can extend this method, let's say, for Gaussian mixture models or other types of decentralized Bayesian inference methods? And second is, does it work in with asynchronous updates, or you're assuming synchronicity?
Yeah, so for the first question, yes, you can extend it for Bayesian optimization, for sure. I'm not sure if you can extend it for GMMs, though. I suspect that you can use some of the tools that I used in GMMs, but I'm not sure if you can, if there is a direct extension to that. And for the second part of your question, great question. And in the results, in my experiments, I assumed that all data communication was synchronous. And that's why I used the standard consensus protocols. But there are consensus protocols where you assume that you may have delays in the communication, you may have asynchronous updates, you may even have resilient consensus protocols where you have a malicious agent attacking your network and you don't know who it is. So yes, you can do that, but you need to use different consensus protocols, of course.
But if you use a different consensus protocol, would it affect the, let's say, convergence of your method, let's say the rates or something?
Yeah, the convergence rate for sure. The convergence, as long the consensus method has convergence guarantees, it will inherit these properties to these methods.
Okay, thanks.
Thank you.
We have time for a couple of more questions, if there are more questions. Okay, no more questions. Let's thank the speaker again.